Okay, so today's lecture will discuss about composition and uses of producer gas and water gas. Then we will be discussing on significance of calorific value of a fuel, where we'll define two types of fuels. One is gross calorific value and net calorific value, and determination of calorific value of either a solid fuel or a liquid fuel using Bohm's calorimeter. And we will solve 2-3 problems related to this Bohm calorimeter experiment. And also we'll be discussing on how refining is carried out to get different fractions from a petroleum oil or a crude oil. First, let us see what a producer gas composes and also its uses. Producer gas is a fuel gas manufactured from materials such as a coal. Okay, so it contains majorly hydrogen, nitrogen, carbon dioxide, and carbon monoxide. It's a mixture of all these gases. Okay, where nitrogen content is more, close to 50%, and hydrogen content somewhere 20-25%, near to sometimes 30%. And then carbon monoxide somewhere 10 to 20%, carbon dioxide some nearly 10% will be there. So these are the gases that are present in a producer gas. Producer gas, it is used as industrial fuel for iron and steel manufacturing, such as firing coke ovens and blast furnaces. Okay. In cement and ceramic kilns also it is used. So how it is produced? The producer gas is obtained where the air is blown over a hot hot coke, a red hot coke. So from this red hot coke, carbon monoxide, nitrogen, carbon dioxide, hydrogen gases are produced in mixture with different quantities. And let's see the composition and uses of water gas. Water gas is a mixture of majorly carbon monoxide and hydrogen, where carbon monoxide it will have somewhere 45% composition, and hydrogen will be somewhere around 50%. How it is produced? Again, steam is passed over red hot coke. So what happens? The water molecule, what is indicated in this reaction, is from steam that is blown over red hot coke that produces the mixture of gases containing majorly carbon monoxide and hydrogen. In small quantities, we have methane, carbon dioxide, and nitrogen. Okay, so water gas mixture majorly contains carbon monoxide and hydrogen. This water gas burns with non-luminous blue flame, and hence it is called sometimes blue water gas also. And the temperature of this flame reaches up to 1200 degrees centigrade. It is used in industrial hydrogenation, manufacture of alcohol, industrial preparation as a fuel. Okay, this from water gas we can obtain different products. Of gases containing both flammable as well as non-flammable gases. Major composition of water gas is carbon monoxide and hydrogen gases, and producer gas will have more of nitrogen and carbon dioxide. And then if you look at the production, water gas is produced by enriching syngas with hydrogen gas and reducing the carbon dioxide level. And producer gas, we can produce mainly via combustion of carbonaceous materials, chemical reactions involved in water gas or reaction between steam and hydrocarbons. And then in producer gas, the reaction between air and carbon. These are the reactions involved. Let us look at the calorific value. Basically, calorific value is the heat content of the fuel. We can define calorific value as the total quantity of the heat liberated by complete combustion of unit mass of fuel. So when I say complete combustion, all hydrocarbon, that is hydrogen content, gets converted to water, carbon content gets converted to carbon dioxide. Similarly, any other like nitrogen, sulfur, if they are present, they will get converted into respective oxides. Okay. Higher the calorific value, more efficient is the fuel. While explaining characteristics of fuel, we told a good characteristic of good fuel is one which has a higher calorific value. Okay. There are different units depending on the type of fuel, whether it is solid or liquid fuel. Depending on that, we can define either joule per kg or kilojoule per kg. If it is a liquid or gaseous fuel, we can put the units joule per meter cube or kilojoule per meter cube. Okay. Earlier we were using calorie per gram or kilocalorie per kg. Now in SI units we are using kilojoule per kg or kilojoule per meter cube. Okay. I said the two types of calorific value we can define. One is gross calorific value or higher calorific value, GCV or HCV, gross calorific value or higher calorific value. Another calorific value is net calorific value, NCV, or low calorific value. How these two definitions are given? Let us see the gross calorific value or higher calorific value. GCV is the heat liberated when unit quantity of a fuel is completely burnt in air or oxygen and the products of combustion are cooled to room temperature. That means two types of heat are getting added. One, while burning the fuel, the amount of heat liberated, plus while cooling the products of combustion, that is carbon dioxide and water, they will have heat content. When you cool those products to room temperature, this heat also get added up. Together, we call it as gross calorific value. It is the amount of heat liberated when unit mass of fuel is completely burnt in air or oxygen and the products of combustion are cooled to room temperature. Okay, that is gross calorific value. Then definition of net calorific value is like this. It is the amount of heat released when unit mass of a fuel is completely burnt in air or oxygen and the products of combustion are let off into atmosphere. What does it mean? I said in the initial slide, hydrocarbon will have hydrogen and carbon when it is reacted with oxygen, that is oxidation is happening, it will get converted to moisture, that is water, plus carbon dioxide. It's not stoichiometric, just I have written indicative reaction. This will have certain amount of heat. Okay, the heat content of these products when cooled will liberate some amount of heat. Okay, it will give out heat. So while burning, heat liberated, plus while cooling these products to room temperature, the heat liberated. Together, put together, it is gross calorific value. In the second case, this heat content of this product is let off into the atmosphere. So it will have the heat content of the fuel burnt. Okay, while burning, what is the heat content liberated? Only that much heat is considered in lower calorific value. Okay. So you can relate GCV and NCV like this. GCV is equal to NCV plus heat associated with steam. Heat associated with steam can be written like this: 0.09 into percentage of hydrogen into latent heat of steam. Okay. Now, from where this 0.09 has come? If you look at the reaction, H2 plus half O2 gives rise to H2O. Okay, this is the reaction of the combustion. Okay, so this is on a gram molar basis. If you take 2 gram of hydrogen can combine with 16 gram of oxygen to give out 18 gram of water. Okay, that means 2 gram of hydrogen is producing 18 gram of water. 1 gram of hydrogen is producing 9 gram of water. Okay, so when you take percentage of hydrogen, this will be 9 by 100, so it will be 0.09. This 0.09 has come from this. Okay, so NCV is equal to GCV minus 0.09 into percentage of hydrogen into latent heat. So this is the equation we can use to calculate NCV. GCV is calculated experimentally by using a bomb calorimeter. The principle involved is very simple, where we take known mass of fuel, place it in a crucible. Okay, this is the crucible, right? So we are placing a known mass of fuel. Okay, then this is placed into a steel bomb. Okay, this is the steel bomb, airtight one. When it is closed, nothing can come in, nothing can go out. Okay, so what they do is they place the known amount of fuel into this, either liquid or solid fuel, weigh and then place it into the crucible. This crucible can be of ceramic or platinum or even other material. Okay, so platinum or ceramic crucible can be used. This is just dropped inside the stainless steel bomb with magnesium wires, okay, connected to a DC power supply. Okay. To ignite, we need DC power supply. For that, magnesium wires are used. Then, using this oxygen inlet, 25 to 30 atmosphere of oxygen is supplied into this, and then valve is closed. Now, the steel bomb, it is airtight, uh, lid is there, so air or oxygen is sufficient amount of oxygen is supplied into the steel bomb, and then this valve is closed. Now this whole setup, steel bomb, is dropped into the bomb calorimeter containing a known mass of water. Okay, usually this is made up of copper material, copper calorimeter, because it's the conductivity, heat conductivity, thermal conductivity of copper is very high. So we use copper calorimeter, and water is measured. Initial temperature is measured using a precision thermometer, what is called as Beckman's thermometer, which can measure up to 0.01 degree centigrade. Okay, and a stirrer is given so that heat is uniformly distributed. When you mix the water, heat gets uniformly distributed across the calorimeter. Okay. Now, what they do after setting up of this, this is further placed into another insulating jacket, and there will be air space. This arrangement is made to avoid heat loss to the external atmosphere. Okay, whatever heat is liberated should be absorbed by only water. Okay, and the calorimeter. Now this is setup is made, airtight lid is given here also. Finally, after placing everything inside the calorimeter, the fuel is ignited with DC power supply. Then what happens? This fuel burns. Okay, while burning, heat is liberated. The liberated heat is absorbed by the surrounding water. This water takes up the heat, and after complete combustion, there are products in this stainless steel. That is, carbon dioxide and water molecules are liberated by the combustion. They have certain heat content. This is cooled. Okay, this is cooled. The products of combustion are cooled to room temperature. Again, they will liberate some amount of heat. Okay, that is latent heat of steam. This heat is also absorbed by water. Now water has absorbed heat liberated during combustion, then heat liberated during condensation of the products. Okay. Now again second temperature is measured. Initial temperature was measured as T1, and final temperature after attaining to room temperature, final temperature is also measured. T1 is measured, T2 is measured, mass of fuel is known, okay, whatever it is taken here. Then mass of water is measured. Okay, so while placing itself, we record the mass of water. There is another component what is called as water equivalent of calorimeter. Okay, this calorimeter, copper calorimeter will have its certain weight. Okay, that is not expressed directly in that weight. What they do is mass specific heat of calorimeter they define, what is called as water equivalent of calorimeter. How do they calculate this? The weight of this copper calorimeter into specific heat of water they will multiply. That will give mass specific heat of copper calorimeter, what is called as water equivalent of calorimeter. This will be known for any calorimeter. Initially that value will be given. Now what all parameters we know? Mass of fuel we know. Temperature 1 is recorded, initial temperature. Final temperature is recorded. Mass of water is known. Water equivalent of calorimeter is known. Then how do we calculate? So simple, heat liberated is equal to heat absorbed. This is heat liberated, it is equal to heat absorbed. Okay, heat absorbed depends on the mass of water, water equivalent of calorimeter. This is specific heat of water, rise in temperature. This is T2 minus T1, delta T. Then mass of fuel. So if you substitute the values, you get the gross calorific value of a fuel, either a solid fuel like coal, or a liquid fuel like a diesel or a kerosene or a petrol. You can measure the gross calorific value. Okay, some values, standard values you should remember. The specific heat of water always it is 4.187 kilojoule per kg per degree centigrade or per degree Kelvin. Okay, so both are same. This is standard value, specific heat of water. Sometimes they will give 4.2 rounded figure. In some of the books you can see that 4.2 as the rounded figure of 4.187. Okay, in old books you can see this as 587 kilocalorie per kg per degree centigrade. This you can see. If you just multiply with this, you will get this value. Okay, 4.187. Sorry, this is converted into joules. 1 joule is equal to 5.187. Sorry, 1 kilocalorie is equal to 4.187 kilojoule per kg. So specific heat you can write this 4.187, or some books 4.2. Now delta T, it can be given either in degree centigrade or degree Kelvin. Okay, so mass of fuel, it is given in kg. sometimes it is given in gram. So if that is the case, then you have to make this equation dimensionally consistent. What do you mean by dimensional consistency? It is bringing all units to the same. Okay, so if this is given in gram, this is given in kg, then you have to make this as kg, then solve the problem. Okay, so this is GCV. Then NCV is equal to GCV minus 0.09 into percentage hydrogen into latent heat of steam. So this equation gives net calorific value. Let us solve one or two problems. Here one problem, one experiment is carried out, bomb calorimeter experiment. The data given is weight of coal, it is 0.85 gram. You can see it is given in gram. Okay. The weight of water taken in the calorimeter 2.35 kg. Water equivalent of calorimeter 0.45 kg. Okay, sometimes they will give this in kg, sometimes they will give this in gram. In that case, you make it same unit. If this is in kg, you convert the gram into kg again, then add. Okay. Then the latent heat of steam, L is equal to 2457. This is sometimes in old books you can refer this 587 kilocalorie per kg is there. You can just convert by multiplying with 4.187. It will give 2457. Okay. This becomes kilojoule per kg. The percentage of hydrogen given is 2.5%. Rise in temperature, that is final temperature minus initial temperature. It's already deducted T2 minus T1, that is 3.2 degrees centigrade. Specific heat of water, standard value 4.187 kilojoule per kg per degree centigrade. Now let us solve this problem. I'll just list out first the values. Meanwhile, you can use your calculator to solve the numerical. M is equal to mass of fuel 0.85 gram. Let us put it in kg. 0.85 into 10 to the power of minus 3 kg. This is mass of fuel. Then water taken in the calorimeter, it is 2.35 kg. W2 is equal to 0.45 kg. Okay. Delta T 3.2 degrees centigrade. Percentage of hydrogen, it is 2.5. Specific heat of water 4.187 kilojoule per kg per degree centigrade. L, latent heat of steam 2457 kilojoule per kg. First, always you write the formula first. GCV is equal to, that is gross calorific value, is equal to W1 plus W2 into specific heat of water into delta T divided by mass of fuel. Now let us substitute this. 2.35 plus 0.45 into 4.187 into 3.2 divided by mass of fuel 0.85 into 10 raised to minus 3 is equal to, if you solve this using your calculator, you can find the value 44,135.9. You can solve meanwhile using your calculator. Kilojoule per kg. Kilojoule per kg. Remember, you should always put the unit. See this unit, now if you look at this, this whole term is kg. This is kilojoule per kg per degree centigrade. This is degree centigrade. Now this degree centigrade goes, this kg goes, this is in kg. What is left out is kilojoule per kg. That is the unit remaining. Now the NCV value, if you calculate, GCV minus, you might be knowing the formula, but while solving the problem, you should write the formula. Always first write the formula, then do the substitution. Each step carries marks. 0.09 into percentage of hydrogen into L value. This is equal to 44,135.9 minus 0.09 into percentage of hydrogen is 2.5 into L value is 2457. This will give, if you solve using your calculator, this will give 43,583.1 kilojoule per kg. Okay, so we should remember always GCV is higher than NCV because the latent heat associated with the condensation of steam is let off in calculating NCV. Okay. Now, I hope this is clear. Let us look at another problem. Calculate the GCV and NCV of a coal sample from the following data obtained in a bomb calorimeter experiment. Weight of coal 0.98 gram. Water weight of water taken in the calorimeter 2600 gram. Water equivalent of calorimeter 368 gram. Latent heat of steam 2454 kilojoule per kg. Hydrogen 5.8%, rise in temperature 2.8 degree, specific heat of water 4.187 kilojoule per kg per degree centigrade. Okay, so let us solve this problem. So what is there? M is given 0.98 gram. Let us put it in kg. Okay, mass of fuel. Then W1 2600 gram. Again, I'll put it in kg, 2.6 kg. W2, put it in kg, 0.368 kg. L value, it is given as 2454 kilojoule per kg. Some books 2457 will be there, some books 2454 also will be there. Okay, you can solve this. Hydrogen percentage, it is given as 5.8. Delta T, it is given as 2.8 degrees centigrade. Okay. Specific heat of water, it is 4.187 kilojoule per kg per degree centigrade. Okay. These are the data obtained from the bomb calorimeter experiment. Then write the formula. GCV is equal to W1 plus W2 into specific heat of water into delta T, rise in temperature. Okay. Sometimes T2, T1 values are given instead of delta T. In that case, you have to write delta T is equal to T2 minus T1 divided by mass of fuel. Let us substitute. W1 2.6 plus 0.368, specific heat 4.187, then delta T 2.8 divided by mass of fuel is 0.98 into 10 raised to minus 3. You can solve in your calculator. You should get somewhere close to 35,500. Okay. Now NCV, net calorific value is equal to GCV minus 0.09 into percentage hydrogen into L. You can substitute the value. GCV is here, minus 0.09. Percentage of hydrogen given is 5.8. L value 2457. You can calculate, it comes close to 34,225 or so. 34 to 25 kilojoule. You can use your calculator and calculate this value. Okay, that is NCV. Okay. See, some of the numerical, they may give GCV value and ask you to find out either T1 or T2, or sometimes they may ask you to find out W1 or W2. No, any other component given except one, you can calculate that one. Okay. Third numerical, weight of coal 0.65 gram, weight of water taken 1200 kg, water equivalent of calorimeter 400 kg, latent heat of steam. This comes to 2457, close to 2457 kilojoule per kg. It will come. Percentage of hydrogen 2%, rise in temperature 1.8, specific heat of water 4.187. So again, you write down the data. What is given? 0.65 gram is there. You convert into kg, mass of fuel. The W1, W1 is 1200 kg. It should be in a gram. So what I'll do, similarly, this I will make it as 0.4 kg. Right, so 1.2 kg, W2 0.4 kg, then S value 4.187 kilojoule per kg per degree centigrade. L value, it is given, it comes to 2457 or 2454 kilojoule per kg. Okay, next, delta T is given as 1.8 degrees centigrade. Okay, percentage of hydrogen, it is 2%, it is given. Okay, these are the data given in this experiment. Let us calculate GCV. GCV is equal to W1 plus W2 into specific heat of water into delta T divided by mass of fuel. Substitute all these values. W1 1.2 plus 0.4 into 4.187 into 1.8 divided by 0.65 into 10 raised to minus 3. You should get the value somewhere around 11,547.7. You can check in your calculator. Close to this value you should have. Okay. Then NCV is equal to GCV minus 0.09 into percentage of hydrogen into latent heat of steam. That is equal to 11,547.7 minus 0.09 into 2 into L value 2457. So if you solve, I should be getting 11,106 as the NCV value. This is kilojoule divided by kg. Okay, kilojoule per kg. This is the answer for NCV. Okay. So like this, you can solve a calorific value of any fuel, liquid fuel or gaseous fuel using bomb calorimeter experiment. Of course, I'm not discussing here for gaseous fuel. We use another experiment, what is called as Boyce calorimeter. A slight different calculations are there. Okay. So we'll stop with this. Liquid and solid fuels, where bomb calorimeter is used to find the calorimeter, um, bomb calorimeter experiment to find the calorific value. Then fuel, we understood the composition, we understood the calorific value, and when you oxidize this fuel, combustion reaction will be there. Okay, for example, methane is a hydrocarbon. Okay, it is a gas. If you combust methane with oxygen, it will give out carbon dioxide and water molecule. So 1 gram mole of methane consumes 2 mole of oxygen for complete combustion. Complete combustion. Okay. So these theoretical values or calculations are very important in combustion kinetics and also in designing this internal combustion engine. So one example I have given, methane. In internal combustion, several such hydrocarbons will be there with relatively higher molecular weight. Okay. So stoichiometric or theoretical combustion is the ideal combustion process where fuel is burnt completely. Okay, one example, methane plus 2 oxygen molecules giving rise to carbon dioxide and 2 water molecules. Okay. A complete combustion is a process of burning all carbon to carbon dioxide, all hydrogen to water molecules. If sulfur is there, all sulfur to sulfur dioxide. If nitrogen is there, all nitrogen to oxides of nitrogen. It may be NO or it may be NO2. With unburnt components in the exhaust gas, for example, carbon, hydrogen, carbon monoxide, the combustion process is incomplete, and that kind of reaction we call it as non-stoichiometric combustion. So any of these components are there in the exhaust gas, then we call it as non-stoichiometric reaction. Okay. We can express the combustion process in this form. This is hydrocarbon, CH, hydrocarbon fuel, plus air. Air contains oxygen and nitrogen. So when you ignite, what happens? Combustion process will go on, producing gases containing carbon dioxide, water, nitrogen, plus heat. It will liberate heat. Stoichiometric ratio is the perfect ideal fuel ratio where chemical mixing proportion is correct. Okay, this proportion, fuel to air proportion is there, no? It should be correct. Then only proper combustion will happen. When burned, all fuel and air is consumed without any excess left over. If you burn the fuel, all fuel and air should be consumed. Okay. If an insufficient amount of air is supplied to the burner, unburnt fuel, soot, smoke, carbon monoxide, exhausts from the boiler, resulting in heat transfer surface fouling, pollution, lower combustion efficiency, flame instability, and a potential for explosion. Boiler resulting in heat transfer surface fouling. What happens? The metallic surface where heat should be effectively transferred to the outer atmosphere. Unfortunately, what happens when this soot, smoke, they get deposited on the inner surface of this heat transfer surface? There is a layer formed that will reduce the heat transfer efficiency of the material. Okay, that is one problem that will cause. When deposit becomes more and more, there is a possibility of explosion because pressure buildup will be there in the chimney. So, and also the unburnt fuels will cause pollution, and it will reduce the combustion efficiency also. Suppose if air content is higher than stoichiometric ratio, the mixture is said to be fuel lean. Air is more, fuel is less, so it is fuel lean. If the air content is less than stoichiometric ratio, the mixture is fuel rich. That means fuel is more, air is less. We call it as fuel rich. Okay. So in case of internal combustion engine, IC engine is internal combustion engine. Generally, air to fuel ratio used is 14.7 is to 1. That means if air quantity used is 14.7 kg, 1 kg of fuel is used. In this ratio, the fuel air ratio is used in internal combustion engines. If you take the example of combustion of methane, of course, the oxidizer will be the air, where the oxygen component of the air reacts with this methane to give out carbon dioxide and water. You can look at this reaction. Methane plus 2 molecules of oxygen is required. So air contains nitrogen and oxygen is there. So 2 molecules of air. Suppose 1 gram mole of methane, if you take 2 gram mole of air should be taken. So air will have 78% of nitrogen and 21% of oxygen will be there. So 2 times of that needs to be taken. And that will give out carbon dioxide and water, and 2 into 3.76, 7.52 gram mole of nitrogen will be liberated. 1 gram mole of carbon dioxide is released, 2 gram mole of water is released, 7.2 gram mole of nitrogen is released. If more air is supplied, some of the air will not be involved in the reaction. That means, excess oxygen will also come out without reacting. That oxygen will also come out in the exhaust. Okay. Take another example, and if you take additional air, now what we call it as excess air. Now equal 1:1, if you take exactly in the stoichiometric ratio, we call it as 100% matching value in stoichiometry. 100% excess air, if you take, it becomes 200% theoretical air. Okay. Then you can write the chemical equation what we wrote in the previous slide like this. For the same methane molecule, for 25% excess air, if you take CH4 plus 1.25, simple. Earlier here it was 1 into 2, so here 1.25 into 2. So 25% excess, 1.25 into 2. Oxygen plus 3.76 nitrogen, giving rise to carbon dioxide, and then water molecule, oxygen, and 9.4 nitrogen. Okay, so when 25% excess air is used, some amount of oxygen is also coming out. Now nitrogen coming out is more. Okay, so this happens when we take excess air. This is not a stoichiometric reaction. Okay. Then I said about the formation of petroleum, natural gas, and coal in the earth crust in the first class. Okay, we obtain this petroleum oil or crude oil from the earth bed. That will have a mixture of hydrocarbons, which will have different molecular weight hydrocarbons containing carbon and hydrogen, but composition will be different. So what we do is to obtain different fractions from this crude oil, refining is carried out. So what exactly we do in refining? So the process of dividing petroleum into different useful fractions with different boiling ranges is called refining of petroleum. The process of dividing petroleum into different useful fractions with the different boiling ranges is called refining of petroleum. So you can call it as fractional distillation. Fractional distillation. Okay. So fractional distillation is carried out continuously in a specially designed tall fractionating tower or column made up of steel trays. Of course, these trays will have bubble caps. When the oil is heated, the vapors will push the caps up, and in between space, the vapors will go out. Okay, so what happens? Lower molecular weight fractions will go into the upper fractions. The high molecular weight fractions will be there in the lower, fractions. So first, what they do is the crude oil is heated in the preheater. Okay, so the preheater somewhere near to 400 degrees centigrade, they will heat the crude oil, and then it is sent into the fractionating column. Okay, this is a fractionating column. I said bubble cap. This is a cap, through which the vapors are entering to the next stage. So this is 1 stage, 2 stage, 3 stage, 4 stage, like this. Several stages will be there. Depending on the boiling point of each fraction, these petroleum fractions are separated. Okay, they get separated. So the bottom portion will have fuel oil, and above that will be lubricating oil. Diesel will have somewhere a boiling point of 270 degree. Kerosene will have boiling point of 170 degree. Naphtha 120 degree. Petrol 70 degree. Refinery gas, it is 20 degree. Okay. So what if you look at the number of carbons of refinery gas, it is C3 to C4. Okay. Number of carbon atoms, it is 3 or 4. Refinery gas will have C3 or C4 molecule hydrocarbon. The boiling point, it will be below 30. And where do we use this refinery gas, which has propane and butane, that is used in the bottled gas. The LPG gas what we use is the bottled gas. The gasoline, the petrol, will have boiling point somewhere in the range 100 to 150, having hydrocarbon C7 to C9, and it will be used in internal combustion engines of vehicles, okay, to produce the power. Similarly, the next fraction, naphtha, will have boiling point 70 to 200 degrees centigrade, and the number of carbons in the hydrocarbon chain, it will be 6 to 11. So the use of naphtha is in the form of several solvents, and also used in gasoline. Okay. Kerosene or paraffin is another fraction where the number of carbon atoms in the hydrocarbon vary from 11 to 18, and its boiling point is also relatively high, 200 to 300 degrees centigrade. It is used as a fuel for aircraft and also for stoves. Diesel will have hydrocarbons 11 to 18, and boiling point 200 to 300. It is used as fuel for road vehicles and trains. Okay, so like that, several classification of these fractions of crude oil is given in this table. You can have a look at that. So uncondensed gases in the range of carbon 1 to C4, C5 will be used in domestic fuel, synthesis of organic chemicals, and then production of carbon black. Okay. And petroleum ether, a solvent in the range of 30 to 80 degree boiling point, and hydrocarbon chain extending from C5 to C6, used as a solvent for fat oil, and also as varnish it is used, varnish. Okay. Now, look at some of these questions, whether we can answer. Ideal fuel has high calorific value is the right answer. Ideal fuel definitely should have high calorific value. At a refinery, crude oil is separated into its components by fractional distillation. Fractional distillation. In fractionating column shown, what fractions come out of A and B. So at this, what is coming out? At this point, what is coming out? At A, it is light gasoline, that is petrol. At B, it is naphtha, that is coming out. Okay, petrol, naphtha. Okay. This is there in the previous slide as a refinery diagram is given. If you look at that, you can find this answer. Petrol and naphtha will be there depending on their boiling point. So what we have discussed so far is we have understood what is the meaning of calorific value and its significance. Higher the calorific value, good is the quality of the fuel. Okay, its efficiency of fuel is high. Then we understood, two types of calorific value. One is gross calorific value and net calorific value. And we can use bomb calorimeter to determine the calorific values of a solid fuel or a liquid fuel. Okay. And also we have solved some of the numericals related to GCV and NCV. In petroleum refining, gas, petrol, and diesel, naphtha, kerosene, etc. are obtained through fractional distillation. So with this, we end this class. Okay, if you have any doubts, you can get back to me with questions.